Today we're talking about inconsistent and dependent systems of linear equations. So when you're working with systems of equations, you'll run into two separate situations, and we're going to explore those situations right now. The first one we're going to look at is an inconsistent system. So I have the system of equations 2x plus y equals 1 and 4x plus 2y equals 4. If I were to go ahead and solve this, looks like using substitution, I would take the first equation here and rewrite it so I get y equals 1 minus 2x. I would then take that 1 minus 2x and substitute that in for y in my second equation, and then I get 4x plus 2 times 1 minus 2x equals 4. Then what I want to go ahead and do is solve for x like usual. I'll get 4x plus, using the distributive property, 2 minus 4x equals 4. If I combine my like terms, what I see is that I end up with 2 equals 4. Well, what I know from many years of math is that 2, in fact, does not equal 4. So something interesting happened here. The first thing we see is that there's no solution. But let's go ahead and take a look at this graphically. I have graphed the two systems of the two linear equations, and then I see that my equation here in red for 4x plus 2y equals 4, and my equation in blue for 2x plus y equals 1. Notice that the lines are parallel. Because they're parallel, they're never going to meet, which means there's never going to be a coordinate that works for both equations. The next thing we're going to do is take a look at a dependent system. So same thing again, I have x plus 2y equals 2 and 2x plus 4y equals 4. Let's bring that over here. And I'm going to use, again, substitution. So I have, with my first equation, x equals 2 minus 2y. And then I'm going to substitute this over here. And so I get 2 times, in parentheses, 2 minus 2y plus 4y equals 4. So then I have 2 times 2 in parentheses, that's going to get me 4 minus 4y plus 4y equals 4. Well, when I take this negative 4y and positive 4y, they cancel out and I'm left with 4 equals 4. Well, unlike the inconsistent system we had before, 4 always equals 4. There's never a time when 4 will never equal 4, unless it's 5, in which case then it wasn't 4. But if I'm going to go ahead and take a look at this data in a different way, let's go ahead and try a table. So I see here I have an xy table, and for my first equation, if x equals negative 1, y equals 1.5. If x equals 0, y equals 1. If x equals 1, y equals 0.5. So when I go ahead and graph that line, I get something that looks like this. However, if we take a look at the second equation, if I plug in negative 1 for x, I will again get 1.5 for y. If I plug in 0 for x, I again get 1. And if I plug in a positive 1, I again get 0.5. It's the same exact line. These are dependent systems. Some of you might be able to notice that if I'm looking at my dependent systems, what happens if I multiply this first equation, everything in this first equation, by 2? I get the second equation. They're the same exact thing. They're the same exact line, which means whatever number, whatever coordinate I plug in that works for the first equation will always work for the second equation. You can essentially imagine them as being two lines right on top of each other. There we go. And that's what a dependent system looks like. So, just to recap, an inconsistent system, your lines are parallel. They will never meet. In a dependent system, your lines are right on top of each other. They're the exact same line.